4. So there's a double breaker for the 240 volt outlets, and then 2 breakers, one each for the computer desk and another one for the radio equipment. And the reason for the 20 amp circuit is if you're going to run it, go ahead and do 20 amps. It's 12-2 with ground. And that way, if I have something that draws a fair amount of current, like a linear amplifier that runs off 120 volts, I can plug it in and likely it'll work fine. There are 240 volt outlets, both 20 amp and 40 amp, just for experimentation and for running some Drake L4Bs. The door into the room is extra wide, and it's a solid core door, again, looking for a little bit of sound resistance. It's extra wide because at some point I'm going to be in a wheelchair and I need a way to roll into here. And that there'll be a ramp, and at the door it's going to be the same. It is the same level on both sides. So it's extra wide, and we're going to try to work it out so there's room in the middle for me to turn around or rotate as needed. Lights in the room, there are track lights with 5,000 degree Kelvin bulbs. There's 3 on each side, and there's a couple on the wall to provide a lot of light in the room, and I haven't got them set right yet. The cameras are mounted on tripods, and those still need a little bit of work. We're still taping and texturing the walls. I'm not good at doing either of those things, but it's getting there. The wall behind me is going to be the chroma key wall. It's going to be all green from end to end. End to end is not very far. The room is roughly 10.5 feet by 10 feet on the inside. It's real echoey because there's not much in the room. I've got the sheetrock up, and it's a concrete slab, and there's nothing much on the ceiling. So nothing to break up the sound. And I'm holding the microphone because it's a good mic, and it's the only one that would work with that camera that I could grab a hold of. So on one side will be the video editing desk with a couple of computers and 3 or 4 monitors. The ham radio desk will be over here, along again with a couple of computers and a couple of screens. Let's see what else. Oh yeah, air conditioning. There's what amounts to an air conditioner that runs in both directions. So it's really a heat pump to provide heating and air conditioning. Heat pumps are not real good for heating, and it does not have strips in it to provide extra heat. But the room is so small that a small electric heater would work fine. It operates on a remote control, which I've kept on the front of the sub panel just because there's a magnet in this thing, and that's a good place to stick it. So I can turn it on, set the temperature, and because it's above the door, it's not easy to get to. The ceiling of the room is about 9.5 feet tall. The other thing I did was to put light switches at the entrance, and another thing is there is a scuttle on the, of course, in the ceiling to provide attic access. It is a little on the small side. It's supposed to be 22 by 30, but it's not a required scuttle, so that's what it is. All right, that's where I am right now. And again, for all those who sent emails, thank you very much. I can't tell you, it meant a lot to me. So for that, I'm very grateful. This is part 2, and there'll be some other updates as I make progress and start to put things in the room, and then I can describe what I'm doing. It is the last day of the year, 2019. Tomorrow's 2020. Hard to believe. 73 for now. I'm Jim, W6LG, for your YouTube Elmer for Ham Radio Basics. See you the next time. And again, thanks for watching. Hi, I'm Jim, W6LG, your YouTube Elmer for Ham Radio Basics. Welcome to my radio room under construction. We've got the wall painted. I should say the walls painted, the ceiling painted, and we're looking for some kind of flooring to put down before we bring in the desks. This device is a game changer for ham radio operators. It's in a black box. It has an LCD screen, a touch screen, and it does some really neat things. Stay tuned, and right after this, I'll open up the black box and show you what's inside.
Whiskey 6 Lima calling CQLO CQ. CQ calling CQ. Hello, CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Inside this black box is a nano VNA, vector network analyzer, and it does bunches of things. I'm going to take the cover off. I put it in a box because I was afraid I was going to break the thing, drop it. So I've got the two coax connectors out the front. This little guy, and with some really neat software written by a guy in Africa, you can do some really neat things. For me, this is reminiscent of when we started to use, it goes back a ways, SWR meters. SWR meters existed, but became really popular in the 1960s, and I think Heathkit had a lot to do with that. Heathkit, Lafayette, Allied, Calrad, a bunch of companies had SWR meters. Prior to that, we would just put up an antenna and cut it the right length and use it. Then we had SWR meters, and we could take a reading. And a lot of us decided that if the SWR was 1-to-1, that's where the antenna was resonant. That may or may not be the case, as it turns out. This device has a bunch of functions. I'm familiar with only part of how it works and some of the things that it does. For example, you can look at an antenna, find the resonant frequency. You can measure the length of coax, which we're going to do. You can measure the loss in the coax, which is hugely important at various frequencies. We're going to measure the loss in some coax connectors yet again, and I'll explain why when we get there. On the floor is a bunch of coax cables, and they go up into the attic. Did not have the time to really test the cables. I'm not exactly sure which one is which at this point, so I'm going to hook this up. It will tell me the length and the loss, and that is really neat. This thing on Amazon is about $50. I think I got this one off of eBay for even a little bit less. I think the device, the construction of the device, I believe to be a little bit fragile, so I stuck it in this plastic box. The software is free. It's unbelievably good. It does a bunch of things. And as I said, I'm still learning how to use it. If you haven't had the opportunity to see one of these in person, if you have a neighbor that's got one, go take a look at it. As I said, it's for $50, it can't be beat. I have had VNAs before. I've had some that were fairly expensive in the range of several $100s. By that I mean $500 to $800. This guy, with the $50 price tag, okay, maybe $60 in some places, and the free software is just as accurate as devices that cost a couple $1,000. Let's first measure the known length of something, do it with a tape measure, and then see how this device measures the same thing. Now, this speaks metric, so we're going to have to convert meters to feet, but we can do that pretty easily. We can use Google or any number of sources. So let's go do that. Let's take a look. Let's see. And by the way, this one is battery powered, but I'm going to hook it up to the USB device will power it. Let's go do two things with this. Let's measure loss in feed lines and the length of some feed lines. We'll do some coax that we know the length of, and we'll do some that we don't know the length of, and we'll look at the loss at various frequencies. And I can decide whether or not the cable that I've got up in the attic, whether or not it's worth connecting to an antenna. It may be so lossy that it isn't worth it. Okay, I'm going to swap this location for a computer desk and a screen capture. Okay, so let's start up Nano VNA Saver. Okay, get my software going here and connect to the Nano VNA. The program scanned and found the Nano VNA on COM3. So connect. It is connected. All right, so I'm going to do the sweep, 10 to 20 megahertz. Let's do 10 10 steps. That's plenty. And first thing we're going to do is run the calibration program. So the calibration assistant will ask us for a short, open, and a load on the first connector. So let's go through that process. Okay, attach the short. I'm going to say OK. Okay, please connect the open. I'm going to do that next. Okay, the open is connected, so we're going to say OK. Okay, please connect a load. I've done that, so I'm going to click OK. Then after that runs, we're going to tell it that's the end of the calibration steps and see if we can get some results. Okay, it said the required steps for port number 1 are done. And I'm going to say apply. Okay, next let's run some known coax and see what it looks like. So let me grab a roll of something and I'll be right back. Okay, I'm going to connect what I have marked as 65 feet of RG213. Make sure the connector is tight, and let's sweep this and see what it says. As I said, there are a lot of things that the Nano VNA does. This is just a couple of them. Its analysis of antennas is really a great thing, and we'll do that in the next episode on the Nano VNA. All right, this is just about done doing the sweep. We're going to click on TDR. It's estimated the length at 64 feet, which is about what I had. Loss measured at 14 megahertz was 1.2 dB, and that loss is the loss for a pulse going out and coming back. So the loss of the coax would be half that amount, so about 0.6 dB. I have a loss calculator set up from KV5R, which is really a nifty one. RG213, let's say 65 feet, or is it 64 feet? Close enough. 1-to-1 SWR, 100 watts going into it. The loss with build an RG213 would be 0.47 or 0.5 dB. And if you put 100 watts into it, about 90 watts would get to the antenna. So the loss of RG213 Belden high quality stuff would be 0.5 dB, and that's what we measured. So the coax that I have is apparently pretty good. I've got 75 feet of RG8X. Let's measure that and see what it comes up with. Again, we measured about 0.6. The Belden would be 0.5, so close enough, especially at 20 meters. So I'm going to connect 75 feet of RG8X. We'll see what that does. All right, the coax is connected, so let's set this guy up. RG8X. Velocity factor is 0.82. Let's go ahead and sweep the coax again from 10 to 20 megahertz, which is what I calibrated earlier. Again, I'm going to click on TDR and bring that up on the screen. And it's estimated length at 77 feet. This is new coax off the shelf, measured at the manufacturer at 75 feet, could be a hair longer. Loss was 2.2 dB, so half that, because again we're measuring the pulse going out and coming back, would be 1.1. The loss calculator from KV5R for RG8X, 75 feet, 100 watts, calculate. For Belden RG8X, it would have been 0.8. So there's a slight difference. not much. It would be a greater difference, I'm sure, at 2 meters or 440. And I don't recommend using RG8X at that frequency anyway. So if you put 100 watts into the coax and you have that loss, about 83 watts would get to the antenna. All right, so we found that the nano VNA was accurately measuring the loss and the length of the coax. I have an unknown. I just want to quickly measure that, see what it looks like. It's one of the many cables that goes up into the attic, and I believe this one is about 65 feet long, so I'm going to connect to that. Okay, I've connected the RG213, one of the ones that I was able to get to run from the radio room at the front of the house to the rear of the house. I believe this is the one that runs the whole length. And again, we're going to sweep it from 10 to 20 to start. I'm just not sure of the length. It could be 50 to 70 feet. Looks like it's going to be in that neighborhood. And the most important thing to me at this point is, what is the loss on that run? That coax is used, this coax is used. I don't know how old it is. Okay, the TDR says it is get the right coax on there. Yep, 64 feet. Velocity factor 0.66 for that kind of coax. Measured loss was 1.2 dB, and again, that's gone out and coming back, so 0.6 dB. So for a coax cable of 64 feet long on the KV5R, just to see what building would be, RG213, approximately 65 feet, 14 megahertz, 1-to-1 SWR, 100 watts going into it. The building would have a loss of about half a dB, 0.48, so 0.5, and would deliver about 90 watts to the coax. So this would be the loss with new coax at about 0.5. And we measured 0.6, so this cable is good. All right, that's a nano VNA, just two of the modes or functions that it does. There are many more, and I'm going to discover them as I go along. The next one I'm going to use is measuring antennas and the impedance, reactance, and get the resonant frequency. So that's going to be fun to do. If this device only measured the coax and gave me the loss, it'd be worth the $50, but it does much more. So we're going to find out about that as we go along. If you have not subscribed, please click that box. Would appreciate it. As I get the radio room set up, I'll be doing many more videos. The room is being painted right now, and next thing tomorrow will be the floor and dealing with that issue and some irregularities in the floor. But I think we can get it done in a day or two. Anyway, thanks for watching 73. I'm Jim, W6LG, your YouTube Elmer, for Ham Radio Basics 73. Bye-bye.
W1VLF. Hey everybody, my name is Paul, and W1VLF, thanks for coming back and visiting me here in the lab. Been away for about a month and a half now, and was in Florida for work for about a week, so that took away time, and man, I got hit with the flu. I'm telling you, I've never been hit with anything like that before in my life. I was in bed for about a week and a half, literally couldn't move. It felt like you were standing in front of one of these fastball pitching machines, constantly getting hit in the head, in the stomach, and oh my God, it was really horrible. But anyway, so that took about 2 whole weeks out of my life where I couldn't really do videos or anything for that matter. And but now I'm back, feeling a hell of a lot better, and I think I will take my wife's advice and get the flu shot next year. Been kind of putting that off for a long time. The other thing is, I'm not sure I'm going to remember how to do this. I got a cheat sheet here, which I don't usually have to use because I just kind of blab it all out. But anyway, so I thought I would try something a little bit easier today. So we're going to take the camera outside in the back and look at the W1 VLF antenna farm, or what used to be the W1 VLF antenna farm, and what hopefully will be the W1 VLF farm back again. But I'll give you that story when we get outside. I wanted to talk about some upcoming videos, should I not get hit with the flu again. I want to do a comparison. A good friend has allowed me to borrow his RSP DX. And if you remember a while back, I did a video between well, the effects of the of an external high-pass filter and how much better reception was when you're running a large antenna on the RSP on the RSP series. So we're going to do a side-by-side comparison. Not exactly sure the order of these videos, but they're going to be coming up. The other thing I want to try is I have some very specific noises here throughout the HF band, and I'm going to be trying the noise cancellation time wave device, the ANC4. And I've done some preliminary experiments with that, and results look pretty good. So I think I might do a quick video and share that with you guys. It might really help some people out. The other thing I want to try is some DIY near-field loops. I use these all the time in my normal work and experimenting around here. These are very, very small, fairly well-balanced loops, and they help you locate noise, the origin of noise, you know, and specifically sometime down to the component level. We won't do that, but we will be able to find out what devices are making noise. So that's another one I want to do. I know there's about 100 open wire feed videos on YouTube, but I want to do one of those. It's very simple to make. I hear lots and lots of guys using the ribbon cable, and I've tried that in the past. It gets wet and tuning changes, not really a great way to go in my opinion. So I'll show you how I made mine. It's similar to how others have, but I got a few little things that make it easier. So that's down the road a little ways when we get some good weather, so I can do it outside. By the way, it's 46 degrees here right now at noon, and the other morning at 9 o'clock it was 1 degree. So things are all over the place as far as temperature goes. And then two other videos that I want to do, which I think were a lot of fun. Of course, I can't do any of them because my antennas are all down. So these will be further into the season. And that is a video on airplane scatter, something I've been kind of messing around with for 4 or 5 years. It's interesting. I don't know if you guys will be able to do anything with it or even want to do anything with it, but using the HF Discovery, well, I guess it's just the Discovery, right? The AirSpy Discovery. Using that receiver and the very high sampling rates, that's probably not the right word, data point rates, you can see some really, really interesting things. That's coming up. And also a viewer, Gene, requested, wanted to know if I would still be willing to build him a WWVB antenna. And the WWVB antenna, stand by, I forgot to bring it out here. I'm just going to grab, I have something on the shelf that looks the form factor anyway. Stand by. Okay, so the WWVB antenna, it uses our best friend PVC pipe, a single PVC T, and there's a screw connection in here, screw-on PVC connection that really allows you to bring your coax up this tube, screw it into the bottom of the antenna, and then screw this piece in. And of course, there's caps on here, and this looks like it's empty, right? Well, and it is, because this is just part of it. And allows you to mount this thing outside, find a proper direction for best best noise, best signal, and it's completely waterproof, easy to mount, and your coax will come out the bottom. So that's one video, and I'll be making that. Show you what goes into that, the ferrite, how I wind the turns, how many turns, and all the dimensions and that sort of stuff. So right now I'm going to take the camera outside, and it's kind of depressing for me to go out there because all winter long, every antenna I have, besides the one open wire fed dipole, has been laying on the ground. So if I if you hear me crying in the background while I'm talking, it's because it's been such a sad winter. So with that, I'm going to head outside and we'll go over what antennas I had, what I have. Oh, I got some pictures too, some before and afters, and some durings of antennas coming down. I don't know, maybe you'll like that, maybe you won't. I always like watching tower constructions and things like that. So with that, 73 for the moment, and I'll pick you up outside. All right, we're outside in the backyard, about 250 feet away from the tower right now. I'm going to zoom in, and that's what I call the saddest sight in the world. 130 feet of Rowan 55 with nothing on top. Had a little mishap here with the tower crew, a little miscalculation, and I'll show you what happened. So I'm going to zoom back out to give you an idea. There's the tower. Some solar panel array over on one side of the house, and right now I'm going to shut off. I'll be back in a second. We'll take a look at the only antenna up there, which is the ladder line fed 300-foot dipole. Okay, well, we're over by the deck, which the ladder line is supported by, and I gotta tell you, the viewfinder in this camera is horrible, because I can't see a damn thing as what I'm looking at. So I'm going to try to zoom in here a little bit. I think I'm going to try to zoom in. This is about 175 feet away, so there's roughly 200 or so feet of open wire feed. Try to get a little bit closer in. And it goes to that side arm there. Everything had to come off the tower, and that's why the ladder line looks very, very haphazard, because it was put back up in a hurry. That side arm has a pulley on the top of it where I can lower the dipole, but during the tower work there was it really didn't get put back properly. I pulled it up there just so I could have something to listen to. So we're going to take a walk over by the tower now, and I'll be back. Alright, we're at the base of the tower right now, and I'm going to slowly go up the tower with the camera, and let's see if this works. Up we go. Now, my God, you really can't see the viewfinder. I think I'll back away from it a little bit and try to get you another better shot. But it's basically, this is a Rowan 55 tower, 129 feet tall, and every nut and bolt that you see here was installed by yours truly, W1VLF, back in the days when W1VLF could actually do this kind of work. Between the gin pole, my trusty Cub Cadet tractor, and about 50 runs up and down the tower, I was able to get this whole thing installed myself. It took about a month, doing it every night after work. And I got pretty comfortable up there. Alright, I'm going to shut off and we'll be right back. Okay, probably 100 feet away with the sun to my back makes it, I mean, in the trees here. I'm in the trees and they're kind of shading me, so go up a little bit. The guy wires are at 30 feet. Can't really see the 30-foot one. Let me zoom in. Can we? No, the 30-foot one is hidden pretty well. 60 feet. And the first real good guy ring, that guy ring there at 90 feet. So the top set of guys and this set of guys are both using the Roan star rings. Let me tell you, those things weigh about 65 pounds apiece, and it was quite a challenge getting them up there. Let's see if I can get a reasonably stable look. I don't know if the camera's focusing or not, but there's the top star ring, the sidearm, and the guy wires going down. So that's a look at the tower. I'm going to intersperse in here some pictures of what was up there before, and eventually what is going up there. I think we're going to walk over and show you the mast that bent during the installation of one of the antennas. And let's go find that right now. So here's the 2-inch mast that held all the antennas that were on the tower, and it looks pretty stable, doesn't it? Until you get up to this point and you find out that there's about a 45-degree curve in that piece. And what happened here is the H-frame of 2-meter antennas, which are mounted right here now, needed quite a bit of lateral thrust and kind of a miscalculation on the tower guy part, because they were using that as the gin pole, and halfway up the pole started to bend. There were 2 guys on the tower at the time. Thank God nobody got hurt, but they were able to very carefully lower the array back down, and no one got hurt. Thank God for that. So unfortunately, there was that was the mast that came out of the top of this tower that supported a bunch of antennas. I'm gonna walk over to oh, by the way, this is the W1 VLF antenna storage / pistol range. And let me just move over to the side here real quick. And I don't know if I can, I wish this was better. And there's the 100-yard range out there. Alright, so we're going to move over to the antennas that were on this tower. Some of them are gone. But here's a 7-element made by JK Antenna in Danbury, Connecticut for 6 meters. That was the bottom antenna. You'll be able to see this when I show you the pictures. Antenna performed absolutely wonderfully. I had lots of great DX, 500-mile range on a regular basis. By the way, this tower, the base of this tower is at about 1,000 feet elevation, perhaps just a little bit more, which is the highest point for probably a mile in any direction. But then when you get up to there, you can see in most directions out to 20 miles, in some directions out to 40 and beyond. So this is a really great VHF location. So back over to the 6-meter beam. So I'm not sure if that's going to be going up again or not, but perhaps. The other antenna that is going back up, definitely, is a 16-element homebrew log periodic that I made. I used to sell these antennas, 8-footers anyway. I made a 16-element because at the top of the tower I really wanted to be able to reach out. and the pattern is very clean. Most FM frequency allocations here will yield, except for the ones that are, you know, very, very local to me within 20 miles, those will yield at least 3 separate stations and 3 compass points, and there are many multiples that will yield at least 5 stations. So it's a lot of fun to go DXing with this antenna. Give you a quick close-up of this. It's a 2-inch booms, 2 booms. The booms are isolated because in the case of a log periodic, the antenna is a feed line. The booms are a feed line. So you can see the mast clamp here is isolated with a piece of, I don't know, what is that, like greater, maybe 9/16 thick polycarbonate. Everything's stainless. The booms are 6063, but the elements are 6061. They're threaded. They go through the boom. And of course, it's spaced each, you know, in all the locations, so that the feed line remains, the boom / feed line remains at the same impedance. And you can see how the element goes through, and then it's nylocked off on the other side. Grab another quick look down the antenna. So that's going back up. And I guess we'll take a walk over to oh, sorry, just had to add this in, the pistol plates. I do a lot of air rifle here too. Main shooting position is right off the deck. I don't know, sometimes hams and shooting go together. Maybe this turns off a whole bunch of people. I don't know. But I thought I'd throw that in there. That's the other thing. That deck is brand new, so that meant all the feed lines that went under the deck had to be pulled out, and it was a real mess. So I'm waiting for spring to be whole again. Let's move around to the H-frame here. So these antennas are the K1FOs, 12 element beams. And there's 4 of them in essentially a 12-foot cube. And this is what caused all the havoc on the tower, having to need an awful lot of lateral thrust to pull these antennas away from the tower. Let's see. Here's number 3. And number 4. The array weighs around 100 pounds with that mast, that middle mast, and the feed lines. Here is the power divider. And everything is kind of ready to go, but it's not ready to go. So it's sitting here on my old satellite TV mount, just mounted in place and tied off, so hopefully when spring comes we can get this antenna array back up again. Here's that mast again, to give you an idea. I don't know, you know, it took a long time to build those antennas. And build the H-frame and square it up, and then to see that thing starting to slide down the tower because the mast is bending. I just thank God that the mast didn't break in half. It's doubled in the middle, right here. It's doubled actually most of the way up, but the side forces were just too much. So there's a new mast over here. This one is a little bit thicker, and I may actually even incorporate another mast inside of this. This is a 2-inch wall, 2 inches in diameter with a 4-inch with a 1/4-inch wall. Let's see if we can do a shot up the tower here. I don't know. I hope the camera focused. I'm going to take a walk out into the woods and show you some of the antennas out there, and that'll be the end of the video. It's a little walk, so I'm going to shut down. I'll be back. Okay, this is the 300 kilohertz and down antenna. It's let's see, each one of those side arms are 8 feet long, so 16 feet. And 16 feet from top to bottom and left to right, and there's 10 turns there taped together, and then you can see those little strings in the middle. Those keep the tension on those turns pulled in. There's a spring. Actually, it's a cheesy old bungee cord, but it keeps it very, very tense, so nothing moves. And this is pointed out to the northwest. This is my WWVB and lower antenna, and I can easily just rotate that on the mast. That holds it above the ground. That's nice because I can come out here with the right capacitor to make it resonate at all the way down to 10 kilohertz if need be. And the other antenna I have that goes northeast southwest is just simply 2 turns. And the other thing is, things are always in motion here. For instance, I am now running Cat 5 cable. As you can see there, look at that rust, huh? Whew. There's a 1-to-1 transformer there for balancing and isolation here on the back. And this is simply just 2 turns. I don't know, maybe 40 feet long and 10 feet high, pointed northwest. Don't use any tuning at all. It's very remote from the house. There's no loss in the feed line really to speak of. And you also, that's the beauty of running balanced feed line. The antenna is balanced. There's a isolation transformer there, balanced feed line in the house, and a transformer there, and you have 3 other pairs. These are really gooey because this is that flooded cable. Hopefully when I get some time I will try to neaten this all up with a box and then bring my other antenna, the 60 kilohertz, the 300 kilohertz and down antenna, all of them both in on the Cat 5 cable. Where am I? There I am. And that used to be a vertical I used a long time ago. And of course, the active vertical. So I guess I'm going to head back towards the house, and if there's anything else that I think it might be of even slight interest, I have a lot of memory in this camera, so I'll grab it. So W1VLF signing off for the moment. By the way, a lot of the common mode noise problems propagating out to this antenna, which I did a video on common mode chokes. With this antenna balanced the way it is, the common mode issue is almost non-existent. It's all a matter of, I guess, good balance. So I have no common mode chokes in this antenna system anymore. It's not coax fed, so that's something to really consider if you're going to put a remote antenna out. Quick shot back towards the house, about 400 feet away. Really makes it nice and quiet out here. And not letting any noise propagate out to the antenna makes it even quieter. So I'm really have settled on no more coax and bringing all antennas back on a balanced. Loops are inherently balanced, or should be. So, and that's what I use mostly out here. I think if I bring the active antenna back online, I think I will make it work through the balanced feed line as well. That's the other thing. Let me just go back here real quick. The other thing is, if you want to have a tuned antenna out here in the field, and which this is not, so it's not resonant anywhere. At least I haven't. I mean, it's resonant somewhere, but two of these wires could be used to run a small gear motor to resonate this antenna. So that's another advantage of running this Cat 5 out. Just thought I would mention that. Just one final look at the main tower here. Can't you just hear that thing screaming how lonely it is? It needs antennas. Okay, so we're over at the one of the guy anchors. There's only one guy here, and that guy's the 30-foot level. This tower was 85 feet when I originally put it up. Then I took it down and went to 129. So this was the original guy point. There was an equalizer plate here, and all the guys were at this point. We'll move over to the outer guy right now, and that's over here. It's guided at about 80%, so that means that this one is about 100 feet out, and oops, let me get out of the sun there. That's the equalizer plate, so that the pull from all the different guy wires equalizes on the anchor rod itself. And let me tell you, digging these holes was a lot of fun. So you have two guys for 120, two guys at the 90-foot mark. These are the ones that go to both sides of those triangles, and those things really keep the top of the tower from torquing. Here's an interesting shot. Let's see if I can do this. And I'm not sure how good that's coming out. I can't see a damn thing. Well, I just have to hope that it worked. Oh yeah, here's an interesting thing. Did you see anything like this? Two pulleys on a rope. This arrangement will allow you, one man, to pull up as much as a 40-meter dipole without ever leaving the ground. And someday, hopefully, I can do a video on that and show you how that works. You have to do a lot of running back and forth between the anchors, but man, you can get a 20-meter dipole, you can get up about 80 feet without any problem. The 40-meter, maybe about 60 feet up, and you never have to have your feet leave the ground. I wanted to show you one more thing. This is the shot. This is the part about the tower that my wife really likes the best. Let me just zoom in. Wow, get a little shaky when you're zoomed in that far. But yeah, I would say by far, every night when my wife comes home from work, this is what she sees, and she says, "Honey, I just love the way that tower sticks up in back of our house." W1 VLF. Okay, so here is the original tower with the two 15-element Cushcraft antennas up on top, the FM broadcast 16-element broadcast antenna, and then the 6-meter 7-element beam. That's what it used to look like. To give you an idea, those two 2-meter antennas on top are 15 feet long each one. The FM broadcast antenna is 16 feet long, and the 6-meter antenna at the very bottom is 30 feet long. Just a quick stationary view looking up the side of the tower. And a little bit better view of that guy point, showing the equalizer plate and the guy wires taking off. W1VLF. Hey everybody, this is Paul W1VLF. Quick Sunday afternoon video here. This is 75 meters, 3 o'clock in the afternoon. And if you look really closely, centered where in the middle of the screen here, you'll see there's a station in there. And let's turn the audio on so we can hear it. Right there. Okay. It's buried. I don't know, would you call that buried? That's a noise from the inverter in my solar system here in the house. So from one of these big systems. I have a 6.5 kilowatt solar panel system. So anyway, that's all the noise that the inverter makes. So I'm working here with the ANC-4 from TimeWave, and I'm going to show you how effective it is. I guess the guy's still talking. Okay, now I just turned the noise blanker, not noise blanker, but noise phaser on and off. Okay, so I'm going to turn it back off again. And it's very selective as to where it's low, where the notch, the noise phasing takes place. So, and I'm going to misadjust it now. Okay, so with it misadjusted, takes careful tuning, but I just wanted to show you this, and I'm going to do a video on how I'm doing it. And the most important thing is, this is going to sound counterintuitive, but quality noise. So I'm going to tune it back again towards. There it is, right there. But as you can see, it's pretty effective when you have quality noise to deal with. And I don't mean the quality of the noise coming in through the main antenna. I mean the quality of the noise coming in through the noise antenna. Here we go. I'm going to shut it off again. And so it's extremely effective. Takes a little bit of tuning, but I'm going to do a video about that. I just thought I'd throw this out there so you guys could see how effective this little box can be when you have the right inputs going to it. Here goes one more time. Oh, there we go. Big signal. But you can see that the noise floor all around it drops off, but not far away, not 100 kilohertz away. So it takes some tuning. Anyway, I'll just leave that on for you there, and I'll mistune the box so we can see what we're dealing with for noise. 73, and this is one of the videos coming up on how to use the ANC-4 and how to get a good quality noise for cancellation. 73 guys, W1VLF, signing off.
Until you get to where the voltage is supposed to be and see what happens. But you can't hurt by changing the caps. There's no two ways about that. I've done it.
W1VLF. Hey everybody, my name is Paul. Thanks a lot for coming back. This is the W1VLF Lab, and this is part 2 in the series, a 2-part series of kicking solar inverter noise in the ass. Can I say that? I guess I already did. I'm not going to edit this out. So last week when we talked about this, I did a really quick video, and the gist of the program here, if you will, is to get a good quality, accurate noise source to add in and invert to the main signal. It does you no good to have one antenna that has just as much noise and just as much signal, add it and invert it. The end result is you're adding noise that is not, that you're adding a noise source that you're not trying to get rid of. So a good quality noise is really what you're looking for. And this is specific to this particular inverter, my particular situation, but the technique it will be the same. So here's what we're using. We're using the TimeWave ANC4, and we're also using a DIY near field loop. Okay, it takes about 10 minutes to make one of these as one source of the noise, and the other source is going to be a current transformer, and I'll explain where each one of these is going to be located and the differences between the two. I'll show you the difference between using this as a noise source, as a noise source antenna, and using this as a noise source antenna. If you look at this, it's maybe 6 inches in diameter. Not really a great antenna for 75 meters. Basically, it's just a one-turn loop. I'll zoom in on so you can see this. This is made out of, I don't know, what is it, 141T or whatever. Let's see what the hard line is. Some piece of hard line that I had laying around. So the idea here is I don't want this picking up 75 meter signals. I don't want this picking up anything except the noise. And so I can take this and bring it very close to the noise source, so it picks up just that noise source, then gets added in through the ANC4, inverted, and I can change the amplitude and cancel just the noise because I'm only adding in the noise. If I were to use another antenna that had similar noise characteristics, the subtraction of the undesired noise would not be nearly as good. And in my case, again, this inverter is putting noise on the AC line. So in that case, I can sample that noise with this current transformer, which is really just a number 2 1/4, 2.4 inch, number 75 core. I don't know, 25 turns on it, terminated into a BNC. That's my noise. That's my secondary noise antenna. This thing certainly works a lot better. Why wouldn't this work really well? Well, because when you'll see how I have this installed later, you're also using the rest of the house as an antenna, and it's bringing in all sorts of other junk that's on top of your AC line in the house. Anything that happens to be dropping noise, conducted noise into the AC power line is going to be picked up by this. Whereas this guy, I'm going to put very close to the inverter, and that will be my noise antenna, and it will pick up very little of anything else. So I'll give you a close-up here real quick, maybe just a minute or two on explanation, and then we'll go outside and see how this antenna gets installed, see how the current transformer gets installed, and then we'll go over to the bench. Excuse me, we're at the Group W bench. We'll go over to the ham station there, and we'll perform some experiments and see, which is better, this or this. And I can already tell you this. But anyway, so I'll do a quick close-up, and I'll be right back. Okay, we're set up here. Here's a quick look at the ANC4. Obviously, power button to turn the thing on and off. And then you have a phase range. If you can't get a good null, then you need, with your source, your noise source antenna, you can hit that button. It'll automatically change this phase control 180 degrees. So if you are trying to get a null and you're right at the very end of one direction, you can click this and it'll put it in a different point, and you'll be able to null it. This has a high and low frequency. For 75 meters, we'll be using the low frequency, and this is the noise gain. So what you're trying to do is you're trying to get an equal and 180 degree phase inversion, so that when you add it together, you cancel out just the noise. It's like adding a 1 with a -1. You have a remainder of 0, and that's what you're looking for here. And this it's very touchy. You'll have to go back and forth with the gain, and back and forth with the phasing control, and the gain and the phasing control. But when you get the null, you'll see how effective it is. In fact, for the 5 of you that watched the last video, it's quite effective. Let's take a look on the back real quick. So on the back we have the main antenna in, and then out to your receiver. So main antenna and then off to the SDR. Power jack, and here's the noise antenna. It's a little inconvenient because they decided to use a phono plug there, which is not my favorite kind of connector. I'm not sure why they went with that. And there's also a hole in the top here where there's a little telescoping mast that comes out of it, 10 inches long or so. And the problem with that is if you use that as a noise antenna, the computer monitor, the printer noise, all those other noises get brought in that are all in the room with you, get added in, as well as the noise offender that you're really trying to get rid of. So that's it. Real heavy. They used a steel case on this. Anyway, so now to the two antennas. So this is just a piece of, I think it's called 141T. I can't really remember. Just a piece of junk coax. You can take a look at the one solder connection. You strip the coax back and solder it. That's it. Extremely simple. It happened to have an SMA connector on it, so I had to adapt that so I can run it using normal coax outside. The other sense antenna, source noise antenna, is going to be this number 75 core with about 25 turns wound on it, soldered to a BNC. So we have two sources of noise. Good quality noise is going to come from this antenna, and reasonable quality noise. You'll see when I hook this all back up. I'm going to take a walk outside and show you how this thing is set up to get the most noise, and then we'll take a look at how this is set up to get the noise that we're looking for. So let me do that, and I'll be back. Look at that thing sticking out there. Unbelievable. All right, we're on our way outside here. Headed over to the inverter itself. I'll give you a shot of that. And got the names covered over with black plastic tape to protect the innocent. So here it is. This is how easy it is. There's the BNC cable. You just hang on. This is a little harder to do with one hand. Okay. So there it is. We're ready for action. That's the outside noise source antenna. So what are we doing? We're very close to the inverter. We're getting a lot of noise from the inverter and very, very little pickup from anything else. So the coax just runs through the window and over to the ANC4. So be right back. I'm going to set up the current transformer, and we'll take a look at that, and then we'll head over to the receiver. Okay, here it is. Extremely complicated. You take your number 75 core with, like I said, 20 turns, 25 turns, and these are the kinds of things that here. The purpose of this video is not to say, well, use 25 turns but not 26. Is for you to do some experimentation and understand and learn about what works and what doesn't in your particular situation. So what do you see here is 3 turns of a line cord wrapped around it, so you have a transformer that couples to the line safely, and your antenna will go to the BNC connector right here. So I'm going to plug this in, and then we'll get on with some of the experiments. It's 12:30, so we're at prime time for power production from the solar panel, which means maximum noise and minimum signals. So here we go. I'm going to plug it in. Where is it? Here it is. It's in. All right, so afterwards, that's where I'll be coupling in for the secondary noise source. So over to the receiving setup now. Hey everybody, W1VLF back again. Now we're over at the receiving system here. And this is what 75 meters looks like. This is a pretty strong signal.
They both do. The little one and the big one has a lithium ion.
Okay, take a listen at it.
So
listen
what's
to
the
it.
issue with the larger one?
Okay. And he happens to be, I'll zoom in here a little bit, right in between two of the really big noise carriers that come out of the inverter. So he's pretty much safe. Not only that, he's 40 dB or so above that signal level. But there are some guys on 3960 here, which I'll go up to. And let's take a listen here. At least there were a minute ago. Let's put the noise canceller in. You can see that it cancels the noise, but not everywhere, just where I'm interested in, right here.
Yeah, and then you just say you're in mark the
Let me
point.
take it back out again.
At the end of the year, right?
Okay, back in. Okay, so here's what I'm going to do. I am going to now connect you to the noise antenna that I'm using to cancel this, so we can see what that looks like. And you'll see that this all these legitimate signals here on 75 don't exist. So stand by 1 second. I'm going to do that. The signal will drop here for a minute, and then we'll see what the noise antenna signal looks like. Okay. Sorry about whacking the microphone here. But as you can see, I guess I could mute that, right? We don't want to hear that. The noise antenna is picking up just noise. Okay? Look, the carriers, all the different carriers that are coming out of the box over there. But those two bigger signals that were on 75 there that we were just listening, one was 40 dB above these, roughly. They don't exist. And that's exactly what we want. So only thing we have here really is the noise coming out of that inverter. So let me switch back again real quick. If I can remember where the wires go. Okay. All right, that should be back again. There's those other signals. Let's take a listen here again. We'll zoom it in. We'll zoom in a little bit. And I'm going to take the noise antenna, the noise canceller out. Okay. And I'll go through this again. I'll do the phasing and gain. So I'm going to purposely mistune it. And I'm going to turn it on. And you can see that I just turned it on, almost nothing happened. So I'm slowly going to bring the gain up. See? Okay, this is not enough gain from the noise antenna. I'm going to bring it up. You'll see the signal dip. Okay, and then a little bit more gain from the noise antenna. No good, too far. So we'll dip that, and we'll go over here to the phase. Make the phase adjustment. Okay, a little bit more gain. Phase adjustment. Gain. Okay. So it really is kind of impressive as to what happens there. And there is a little bit of loss through this box, as someone in the last video mentioned. So the signals aren't as strong coming through the box. There's like 6 dB of loss through it. But I guess if you were listening to somebody, you could tolerate that a lot better than that. Okay, so what I'm going to do now is I'm going to disconnect my noise antenna. Okay, so I didn't do anything except for disconnect my noise antenna, and that shows that without that noise coming in that particular phase, in that particular amplitude, it's not working. So now what I'm going to do is disconnect from the really good noise source outside. And I'll leave this thing running while I do it so you can see what happens. And we're going to go over to the AC coupler, the current transformer. So give me a couple of seconds here. And I'm not going to pause it, but I want to show you that when I do hook up to that, the phasing and amplitude adjustments are completely different because it's a different noise source. Also, kind of notice right down here. Let me open that up a little bit.
That's good information. I need to do something.
All right, down here, minus 55 or so.
I'm already spending a lot of
So
money.
this is about as pure a noise source from that inverter I can get. The one coming off the power line won't be so good. I'll be right back. Yeah, hitting any other room to disconnect. Without tripping. Okay, now we're connected to the current transformer, and I'm going to do the same thing with noise, with the gain and the phasing. And let's see, change the phase. Okay, you can hear other noises that are riding on the AC line in there. Okay. Noise canceller off. Noise canceller on. Where'd those guys go? Well, maybe they took off. Or maybe I just don't get enough canceling to so you can see that you can hear them, but you can also hear the rest of the noise that I brought in with that inferior noise source. I'll try to cancel it best I can. So canceling does not yield a nice, quiet background. If I didn't have a whole bunch of other noise on my power line here, it would work, but it's just not satisfactory. Look at the rising and falling of the noise floor there. And I can't really get a super clean null. I'm adjusting it here. I mean, it does null it. Maybe a stronger signal would be okay, but the residual noise floor, because I don't have a good, the residual noise floor, because I don't have a good clean noise source, is not really that great of a solution. But if you had this signal right here and you had somebody 10 dB above the noise, let's find somebody else. Somebody right in the middle of them. I hear somebody right here. Oh no, that's the same one. So it does work, not as well. So I'm going to switch back real quick. Hang on. So you can see how bad how it's actually worse now, because I'm adding too much inverter noise. So I'm going to turn the gain down and play with my phasing here. Let's spread it out a little bit.
a year, and if I can't make that 3.5% back in a year, I'm not doing very good investment.
So there it is.
So, yeah, you gotta eventually pay tax on the untaxed money. Either you take it out, or when they force you to take
Anyway,
it out.
that's about the end of the video. If you made it this far and you found this interesting, maybe you could go back and look at the first video, which was part 1, and just mute this. Maybe give me a thumbs up if you thought it was interesting, or a comment, or you could do that better if you just did X, Y, or Z. But most importantly, if you could subscribe and hit the notification bell, I would appreciate it. This video didn't take all that long to do, a couple hours, but if I do get more than 5 people watching, it gives me incentive to do others. So I really appreciate it. Thanks an awful lot, everybody, for watching, and leave a comment and hit the subscribe button and a notification bell if you would, please. This is W1VLF signing off from the Noise Empire of Connecticut. Hey guys, one more thing I wanted to show real quick, and I should have shown this before, but I totally forgot about it. Let me turn the volume back on.
Yeah, you got a pretty good signal there.
Okay. And I'll turn off the noise canceller, and I'm going to go do the most important thing, and that is shut the solar system off. Stand by. 3, 2, 1.
Yeah, that's good. You know, I was just talking
So
to
that's your most
Larry and the
effective
guys
noise
down there.
canceling right there.
His,
W1VLF
it's 600
signing
watts. He
off.
said that no
This
one
time I
feels the
really mean
difference.
it.
He used to
W1VLF. Hey everybody, I'm Paul, W1VLF. Welcome back to the lab. And as you're going to see in a couple of minutes, you will we'll go over to the computer and the SDRs, and we'll be playing with this ferrite loop stick here. You'll see the video and you'll hear WWVB, and this is going to be a multiple part series. I'll show you how I make these loops. I'm afraid to even show you this because it's just laying on the bench here. Ground level is about where the window is, so the antenna is below the level of the earth right now. I just took one of my old prototypes, which is essentially the same as old meet the new prototype, same as the old prototype. But what it is a ferrite loop stick, and I'll go through and show you everything, how it's made. It doesn't look anything like this, but this is a fundamentally the basis. So I'll show you that up real quick, and try not to laugh too much. I will also show you some pictures of the end result when it's all tuned up and sitting in the proper case and everything. So please don't judge by this, and give you a quick look at it. This is basically just to have something here that I tuned up so we can go to the other room and take a listen to it, give you an idea what's going on. So part 1, WWVB, 60 kilohertz. Give you some close-up shots now, and I guess that's it for now. Okay guys, I'm back. I got to do this handheld because I just can't set up the tripod. And it's late. I haven't eaten yet, so you know W1VLF gets pretty grumbly. But and you knew this wasn't going to be pretty. But there's essentially the coil. It won't really look like that. This middle piece won't be here. This was a kind of an in-house portable thing that I was building. I have a coupler coil that fits on top of it to sample, and I have a couple of different taps that allows me to get the maximum out of the antenna that I possibly can. This thing shows about 18 inches, but it's really going to be only 16 because this middle piece won't be in here. I use a capacitance box to get roughly in the ballpark, and then I have a small, that's like 700 picofarads, 0 to 700 picofarads in parallel with that. So basically this is what you're listening to in the other room, and just wanted to show you. Again, please don't take this as the finished product. This is just one of my old coils I had laying around, and I wanted everybody to see what it looked like. So give you a couple of quick shots of what the antenna looks like when it's finished, and then we'll go into the SDR audio. By the way, I'm using the HF Discovery in the other room. With the preamp that's in there and the low noise front end on that thing, I don't know, I really enjoy that receiver. So a shout out to Yusuf for building that thing. So anyway, enough blabbering from me. I'll show you what the end product looks like, and then we'll go over into the other room. 73 W1VLF. Hey everybody, W1VLF, Paul here, sitting behind the radios, and wanted to show you a little something, the next project that's going to be coming up, and it's a WWVB antenna, 60 kilohertz. And this antenna is, let's see, what is it, like 16 inches long, and it's right now it's laying on my bench. You're seeing the video of the received signal here. I'm in Connecticut, so it's about 1,800 miles away. Let me just pop the audio on here real quick. You can see it's about an S7 on peaks. And the noise floor, if you look over here, is roughly an S1. It varies throughout the night and throughout the day. But a lot of guys have been asking me. I used to make these antennas. I used to make these antennas and sell them many years ago. And one of the viewers, Gene, asked me if I could build one for him, and I did. And I thought, well, maybe this would make an interesting video for folks. So this is the antenna. It's raw, just laying on a bench, wires hanging out of it all over the place. It's about 3 feet below the ground at this point. Because it's in the basement here, so get this thing outside, and it's much stronger signal, and again, better signal to noise ratio too. Here, I'm going to show you something really cool. Let me zoom in on this a little bit. See all this crap over here? The antenna is in the other room, right? Watch when I shut this bottom off. I'm running 2 monitors right now. I'm going to shut this bottom monitor off. Gone. I'm not sure what this other one is here that's left over. I don't dare shut off the monitor I'm watching while I'm talking here, but it's just okay. Just turn the monitor back on. It's just really amazing the amount of noises that are out there. So this is it. S7, S6, S7, daytime, sometimes S5 to S9, and stronger on an 18-inch ferrite loop stick in the other room. And so I figure I would show you the process, how I wind these, how I tune them, the end result, and I'll shoot a little picture out here in a second at the end of this video. But any questions, let me know. The part 1 of this probably be a couple of parts, because there's quite a lot to it, and there's a few stages where you have to wait for things to cool, because there's a little bit of hot glue involved. I try to make these so that they're not fragile, but obviously you don't want to be dropping them onto a concrete floor. Anyway, there it is. I'll let it run for a couple more seconds without me blabbing away, and I'll show you what the end result looks like when they're done, and we'll see you on part 2. W1VLF. Hey everybody, my name is Paul, W1VLF. Thanks for coming back to the lab here. Today is going to be part 2 of building the WWVB antenna. And a couple things that we'll cover. First of all, sorry it took so long. Things have been just really hectic and I have not been able to get out to the shop here. But thanks a lot for staying with me on this one. I appreciate it. Today we're going to cover the parts list to build the housing, to build the actual coil, the ferrite rods, all that stuff. We're going to wind the coil. We're going to look at how much inductance we end up with, what we need for capacitance to resonate it, how we sample the signal from the resonated coil. And we're also going to look at the evolution. I put together like a little PowerPoint thing, and it'll show you how we go from a coil to a ferrite loaded coil to resonating it, sampling it, what exact values do we need, and how close do we come to those when we're winding these components. So that if you change some things in this design, you'll at least know a direction as to how to get back to making it work. The last part of this video is going to be actually tuning the antenna. We have basically the core of the antenna here right now, with the sample winding here. It's going to be mounting it in the housing. Okay, getting it mounted in the housing here, bringing the wires out, and how we get to get this T together and all the right lengths. All that stuff will be in the parts list. And then finally, we're going to tune it up. Show you the procedure for doing that with your laptop and your SDR. I use the Discovery because it works really well. It's nice and small, light, easy. Take it portable with you, all that neat stuff. And then we're going to do a remote test. We'll stick it out, not on the bench here like you're used to seeing this, but out in the antenna field, 300 feet away from the house. So we'll get to see what it looks like coming through that coax cable 300 feet, and also in a nice quiet environment. So anyway, I'm not sure how much I have for this opener here. Anything else? Well, I do have all the components, the PVC pipe and the T, and the end caps and everything, and all this is described in the parts list that we'll go over there in a couple of minutes. The parts list, it covers where to get the ferrite rods and just about everything that you need to know. What it doesn't tell you is where to get this number 24 wire. I use number 24 because I have about 25 pounds of it on hand. If you use number 22 wire, a little bit bigger in diameter, you're going to find that you have less turns. The 15 millihenries of inductance will not be there. It'll be a little bit less because your wire diameter is bigger and you have less turns. But using the calculator that we'll show later, you'll be able to figure out how to know approximately what capacitance you're going to need for this. So I guess I rambled on long enough. I guess we're going to move into, the funny part about doing these videos is you can't do them in order. You have to do all these different segments and then try to put it in order. So being an OB and an old bastard, I sometimes can't remember what I said in the previous piece, so bear with me on that. I think we're going to move now into winding the coil. And the end part will be kind of the tutorial of how this thing ends up being an antenna and kind of an evolution. Okay? Thanks a lot. Let's move along. Okay, so in this part of the video, we're going to glue up the essential core here. So I've got, let's see, 16 inches. 16 inches of the 1/2 inch CPVC. You'll see this in the parts list. 2 end caps, one of which I drilled a small hole in, and that's going to be for later on. It's going to serve 2 purposes actually. For later on when I wind this coil on the lathe, and it'll also let the air escape out from this tube when we do this glue up. So right now what I'm going to do is I'm going to glue the permanent end on with the PVC cement. and then I'll do a little bit of a close-up and show you what's going on with the two cores here. You can use multiple cores. You can stack cores horizontally, lengthwise. What's going to be critical is when we get our big coil wound is that nothing moves in relation to anything else. Even if there's a 1/4 of an inch gap in between these two, they don't have to be making an actual electrical contact as long as that gap doesn't change. You know, we can't just put the two cores in. And also be really careful. You drop one of these even from 6 inches on a concrete floor and it's gone. There's no getting around it. So there's a little bit of play in there because I haven't put the cores on tightly yet. But what I'm going to do is we're going to put a little bit of glue, Gorilla Glue. I think it's, I forget what the name, what actually it's called. I'll show you the bottle. But it expands. And so this little hole, when we get the cores in there, is going to let the air out and probably some of the glue too. But what's important is that wherever those cores land in there, that they don't move. So do a quick glue up here, show you that part, and then we'll move on. Okay, so here's that glue I was talking about. It's Gorilla Glue. Bonds virtually everything, but it's one of those expanding glues, and you need a little bit of water to make this work. I've already put one end on the PVC pipe here, okay, and so my end with the hole in it is yet to go on. So what I'm going to do is I'm going to put a few drops, maybe a little bit more than that, down the center of the PVC here. When it finally gets, by the time it finally makes it to the, okay, alright, wipe the end of that off, and then I'm going to kind of wet up my cardboard here so I don't mess up the Group W bench any more than it already is. And when these go in, they'll kind of slide in slowly, right, and I probably put a little bit more in there. And the whole reason for this is, again, this is that expanding glue. Okay, and we'll wet this up a little bit. Okay, twist it. Okay, you can see that goes in slowly now. This end here is pushed on all the way too, this far end. And so the only thing really left to do is to glue this, glue this up. Clean that out so we make a good connection and push it on nice and tight. Okay, and I'm going to push this down so it's very tight. Okay, so you can hear already that it's not really moving. Okay, so that little hole is for expansion, that's to let air out. And you're going to end up with some glue on the end of this from the expansion, but just clean it up. So the only thing left to do now on this is to stand it up for a couple hours in a vertical position. Well, you know how hard it is to look at a tiny little screen and hold all this stuff in the right spot? Anyway, I put it in a vise right here, and I just let it stand. I don't squeeze it a lot, just enough to keep it vertically, and then we're done. So next step is going to be winding the coil, but I've got to let that glue expand and cure. So I'll be back after that's done. It's going to be a couple hours, but for you it'll only be a couple minutes, or even less. Okay, so we're out at the lathe, and this is the way that I wind them, because I have access to a lathe, but also because when I was making 10 or 15 of these at a time, it got very, very cumbersome. So here's where that tiny little hole is going to come in handy. I'm going to put it in between the chuck here, and let me just tighten up the chuck a little bit right there. Not enough to crush it, and we'll put the center Okay, so now we have a nice tight arrangement. I left about 5 feet of wire here on the end I'm going to wind from, because we're going to need that to go down inside the housing and come out. So we'll leave that there. The truck is going to be turning away from us like this. Actually, you know what? Let me just pull that out of there just a little bit more. Let's get that out of there just a little bit. Right about there is probably good. Okay, so that's a center that's going to allow it to spin. This is going to be what we drive from. By the way, don't ever leave that in there like that. That was a mistake on my part. You forget that in there and you turn the lathe on and that chuck key will come flying out. So I'm going to be winding in this direction where the chuck is moving away from me. So I'm taking my extra piece of wire and I'm going to wind it around the chuck here. Alright, to get that out of the way. Alright, yeah, just fold that under so it won't move. Okay, and away we go. It's always a little bit nerve-wracking when you first start it. You want to make sure that the wire is feeding properly. I think there's about 800 turns, so it's possible to do this by hand. But not much fun. So as I come up to the end here, I'm going to have my hand on the power switch, and right when I get to the end, I'm going to shut it off. Okay, good. Hold that in place while I rip off a piece of tape with my teeth. That's very professional, isn't it? Just tape that on there temporarily. Okay. Alright, we're going to need another couple of feet extra on this end too, so we'll break that wire off. Okay, and I'll just run the lathe for a couple seconds just to wind that up. Okay. Alright, so now we have to tape this down. So I'm going to start with the tape over here. Get it relatively tight. Give it 1 or 2 turns by hand here. Okay. Let's see, back it off a little bit. Okay. All right. So, we're done winding. So I'll unwind this piece here. Okay. And we'll unchuck this from the lathe, the 3-jaw. Okay. And there's our finished coil. This will carefully undo. And now we'll go over to the bench and we'll check this on the LCR meter to see we should be somewhere around 11 millihenries. All right. Okay, we're over at the LCR meter, actually a couple of LCR meters. One hit, if you're interested in experimenting with this kind of stuff, it's really handy to have an LCR meter. These are quite old. There's a lot of very inexpensive ones out there today, but being able to measure L and C with reasonable accuracy is really cool, and will help you in a lot of your experimentation. So here's the coil. Okay, I had to do a quick edit there because holding the camera and connecting the wires was a little difficult. So just some 4-wire leads here and back up, and you could see the estimate was 15 millihenries, and we're at 14.5 millihenries. So we'll pop that number into our calculator afterwards and see how close we come. While we're over at the LCR meter, I thought I would take this variable tuning capacitor that I have. This is how much capacitance it takes to resonate that loop to 60 kilohertz. So I'm going to bring that over to the LCR meter and check real quick the value of that, and then we'll have both values to plug into our calculator. Okay, so we're over at the calculator here now. There are lots of different electronic calculators out there. This one seemed to work out pretty well, and it also shows the LC circuit at the bottom. So, of course, you have all your obligatory, commercials and whatnot here. So, but let's roll down to the meat of the program. So, when you first fire up the calculator, it calculates something evidently in the audio range. But so our inductance, we want to be what? Let's see, 14 point. Let's call it just 14.8. And not microhenries, but we were in millihenries, so we'll select that. And we had about 480 picofarads, not microfarads. So we'll go to pico, and we want our answer to come out in kilohertz. So let's hit the calculate button and find out where we are. Okay, so 59.7 kilohertz. Based on our actual values of 14.8 for the coil and 480 PF for the capacitor. So this shows us that we're in the right ballpark. Part number 3 of this video is going to be the actual tuning, which may be the most difficult part for people to do, and I'm going to try to show that by using it to tune the noise floor. But this allows you to say, I have this coil of this inductance, this amount of capacitance, where am I going to land here, and vice versa. You could say, I think you can in this 60. Let's see. Let's do this 60 kilohertz in kilohertz and calculate again. Well, you have to get rid of one of these values, so turn that back to 0. Calculate it. 475 picofarads. It's now calculating that value. So you can run the calculator a couple of different ways. So if you can measure one or the other, you'll know what the third value is. Anyway, back to the video. W1VLF signing out. Wanted to take a couple of minutes and show how this antenna evolves. And in the first slide here, you have basically just an inductor, raw inductor. And this is the 16-inch inductor that we wound over on the lathe. Right now there is no core in it, and I really don't care at this point. What we're interested in is what we end up with when we wind those 800 turns. In each one of these, you'll see a red arrow showing what we changed from the previous slide. And in this one, we've inserted the ferrite core. And now we're going to measure that. And at the bottom of the screen, you can see 15 millihenries, which is the size of the inductor, the inductance for this antenna. The next component added is the variable capacitor at 480 picofarads. That value I determined empirically from building these over the years, But as you saw in the previous parts of this video with the calculator, that component can vary based on the amount of inductance in the coil. And so you can arrive at that using that calculator. It gets you in the ballpark. Here it ended up being 480 picofarads. I show it as a variable because that's what that's how I tune the antenna to the exact frequency. Later on, I would measure what that capacitor value is in real world, what the capacitor value actually is, and then I would build that with silver mica capacitors so you wouldn't obviously have a variable capacitor out inside that housing. So now that we've built our parallel resonant circuit, and that's really what it is, the only difference between this parallel resonant circuit and one that you might find inside of a radio is this one is designed to receive frequencies, to let the radio frequency magnetic fields cut into it and give it an output voltage. And if that's the case, we need to extract that energy somehow, and we do that with 10 turns of wire in the very center of the core. I've tried 20 turns, less turns. You can change that impedance transformation and the return loss, but to get the proper bandwidth that we're looking for and to extract as much signal as possible, 10 turns seems to work really well. Alternately, you could tune this antenna and put it near a receiver that already had 60 kilohertz, small 60 kilohertz, like an atomic clock antenna or something like that. And if as long as it was in the field of this resonant circuit, that would work as well. I've done that quite a few times in the medium wave bands. But in order for us to extract that signal and then put our antenna out at 300 feet, we need that coupling loop. In this slide, we just show that the SDR receiver, whatever you're using, or even standard receiver, is coupled to those 10 turns. Not much really to report on this slide here. Whoops, quick note, look there, it says 11 millihenries. That really should be 15 millihenries. Quick slide here just to show the various components that are used in building this antenna. They're called by their generic names, not by any particular company's part number. This way here you can go to either Home Depot, Lowe's, Menards, or wherever you're going to get your PVC components from, and just look for these pieces. A few more things you'll need here. The ferrite rods. And these are the 10 millimeter by 200 millimeter 400 permeability Russian surplus knobs. Russian surplus rods. There's a lot of different companies over in China selling the same diameter and length. I've never used those, so I don't know if you put those into this circuit if that'll work. I bought a ton of the Russian ones, and they've always seemed to work. They're not they're not cast that well. They're not perfectly straight, full of little lumps and bumps, but you're never going to see that when it's inside the housing. An SO239 UHF chassis mount has to be the 4-hole type because that's going to be important when we put the end of the antenna on, and it will hold that connector in place and shield it from the weather. That's important. And then the third is I use number 24 wire, which if you don't know if you have number 24 wire, it's approximately 20 thousandths in diameter. And you need about 120 feet of that. You could go through the calculations. There's about 800 turns at 20,000 20 thousandths diameter per turn, and the rod is, I think, the CPVC is something like 5/8 or so in diameter, and do the pi formula and come out, but you're roughly going to need 120 feet for the antenna. A lot of turns. Here's a screen capture from eBay showing the actual rods. I think this is even the person I bought these from. Although they're a lot more expensive than they used to be. These are the either Russian or Ukrainian knobs that, I keep saying knobs, rods that came on the surplus market. These I know will work in this antenna. The other ones that claim to be exactly the same from China, try those at your own risk. I really don't know if they're going to work or not. Here are the dimensions of the pieces of PVC pipe. Everything on this page is 1 inch. and you can see basically how it goes together. I'm not going to show gluing the whole antenna together. That's pretty straightforward. Anybody who's played around with PVC pipe understands that. But you can look at this page, and then you can go back to the parts list and order up what you need. So 2 pieces of 1 inch PVC, 8 inches long, 1 inch PVC, 8 inches long. There's the T, the 2 end caps, the male and female adapters, and then the PVC pipe at the bottom, and then another little section of 3 inch long 1 inch PVC. Parts list for that inner core, just a single piece of the 1/2 inch CPVC with a couple of end caps and 16 inches long, and that's the where the ferrite rods go inside of and what we wound our coil on. Just a quick note here, the antenna will be broadside toward WWVB, not off the end off the end caps. So when this thing finally gets orientated, it'll go almost east-west for me here in Connecticut. Okay, that's it for part 2. Appreciate everybody sticking with me this long. Part 3 is coming up, and in part 3 we're going to be tuning the antenna, mounting it in the housing, and then doing an on-air test with it located 300 feet out in the woods, so we can see how the antenna will perform then. If I can ask you please to subscribe and give me a thumbs up on this video. I think if you give a thumbs up, if you enjoyed it, that it will get promoted to other people. It's a big incentive to do more of these things. Thanks again. This is W1VLF, and I'm signing out. W1VLF. Hey everybody, Paul, W1VLF here. Welcome back to the lab. I know you're saying, can I get rid of this guy or what? Twice in one day. Had a few free moments here, and I wanted to do a quick video on something that I've been messing around with a little bit, and that for a long time, and that's aircraft scatter. Everybody's heard that, right? You're listening to either a radio station or your ham friend on 2 meters, and the signal starts pulsating up and down, and then faster and faster, and his signal will come way up out of the noise, and then all of a sudden slowly fade back away again. And a lot of that, or at least some of that, can be due to aircraft scatter. And that's when the station and you are directly in line, and in an airplane, a large aircraft passes within it. So we're gonna just head on over to the ham shack there, hook up the air spy, and these signals are typically above the FM broadcast band between I think 110 and like 118 megahertz. So I'll do a little explanation over there, but take a look. This is interesting. I mean, I find it interesting. You guys might think this is like watching paint dry, but this is kind of in the series of neat, weird stuff that you can do with your air spy discovery. Okay, back to the ham shack. Okay, so we're back over at the ham station computer now, and we have the HF Discovery tuned to right up here, 116.6 megahertz. So we're just above the FM broadcast band. And what we're looking at here in the center of the screen at 116.6 is a small airport in Carmel, New York, and that has a VOR. And I'll pop open, let's see here, we'll go back real quick. So VOR is a navigation aid for pilots. Typically they're just above the FM broadcast band. And the nice thing about these is, and we'll pop back down here, we'll pop here, is that they're a constant carrier. So any sort of propagation that takes place, they're the same constant level transmitting. So anything that happens between you and that airfield, you'll be able to see that on the screen. And you'll see some of these things. If you look right over here to the right, you can see an aircraft that's passing between me and the airport. So I'm going to switch back for a second to show you where that airport is. By the way, you can go to airnav.com and you can find airports within 50 or 100 miles. Here is this airport. Distance between myself and this airport's about 46 miles. It is not line of sight. There are some hills in the way, and I am using a 160 meter dipole right now for an antenna. So you don't need anything really fancy to do this. So what are we seeing here? We're seeing the carrier itself, and we're seeing the two sidebands. The lower sideband that's 30 hertz away, the upper sideband that is 30 hertz away in the upper direction. And all this information that you're seeing here is, I'll put the mouse over here for a second. What you're seeing here is a reflection off an aircraft, and you can see it drifting lower in frequency. It's high here and low on the other side, and the aircraft is coming in between myself and the beacon or the VOR. Everybody's heard this, where you're listening to an FM station or something, and the signal starts going whoop 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 faster and faster, and then you get this very enhanced signal for about a couple of seconds, and then it drops off again. Several flights are going by right now too. Let's go back to. Sometimes the old guy just loses it here. So these flights are. Here's Long Island down here. I don't know where these flights are, but if a flight is going diagonally across or coming into the path, as it's approaching me, it gets higher in frequency, or starts off higher frequency and then drifts lower. You can see here all the way out, I don't know, this filter is set for 60 hertz wide. So you can see the two sidebands, the upper and the lower sideband, those 30 hertz sidebands. And the reason why you do this is because you use one of these VORs is, first of all, they're plentiful. You can find a list of them anywhere in the country. Chances are there's going to be one that's far enough away so that there will be air traffic between you and it. And it has actually no modulation, except for the two 30 hertz carriers. If you were to try to do this with an FM broadcast station, you would not be able to see this propagation effect, because the 200 kilohertz wide FM broadcast station, there would just be all this noise in there and you wouldn't be able to see it. So a quick setup here. I'm using AirSpy and I can't do this with console. I can't get the resolution high enough to be able to do this. So real quick, we're at 384 kilohertz of bandwidth. All the preamps and stuff are on. I don't think that makes much difference because we're up in the VHF portion. Let's see. The filter bandwidth is 60 hertz. I did that just to show you that the two carriers are one below and one above, are 30 hertz up above and below the carrier. We're not going to really. Oh, we'll take a listen. All you're going to hear is a single tone. So we'll mute that away. But what is important is this right here, this resolution. This is what I typically use. You can go one more step higher. And look at this real close. Here is 829, 828. These are about a minute apart. So these little propagation anomalies take several minutes to take place. And if you think about amplitude here, look at how strong this is. Much weaker ones here and here. Now, I know a lot of people are going to think this is about as much fun as watching paint dry. But there are times when I had my big log periodic for the FM band up in the air, and I could point towards airports that were 300 miles away, and I could not see any signal at all. But when an aircraft went by, there was a huge enhancement for maybe 30 seconds, and then it would drop away. So you essentially would see just these diagonal lines and no main carrier in between. So this is just something I wanted to throw up real quick. Something I've been kind of doing for a long time with the big antenna up on the tower and not using this 160 meter dipole. I can see maybe 20 or 30 of these different VORs around in different directions. And when you point down towards New York City, and there's a lot of air traffic passing through, this screen just becomes totally jumbled with nothing but diagonal lines. The size of the aircraft makes a difference too. Obviously, the larger the aircraft, the more intense this reflected signal is going to be. And it's about 8:30 on Saturday night, so there's not a lot of flights out there. If I were to do this on a Monday morning at, say, 7 or 8 o'clock, you would see incredible amount of traffic in here. So anyway, just something I wanted to show you guys. You could check out where the VORs are on airnav.com. Pick one that's, 50, 100 miles away. Monitor it, and you'll be able to see these little propagation anomalies. Any questions, leave me a note in the comments, and just shoot this up on YouTube here real quick. 73 guys, W1VLF, signing off. Hey guys, there was a little bit more activity after I came back from the ham computer, so what I thought I'd do is just take a few quick snapshots. There's three of them here, and each one's about 10 seconds long. You can take a look and see the activity, the aircraft activity that was happening while I was shooting. This particular one has a very, very strong signal in it. So anyway, just wanted to show you a couple more of these. Try this out and see what happens if you've got some really boring day that you don't have anything better to do with your life.